Today we are going to discuss expansion index test, which is also called as EI test. This test method provides an index to the expansion potential of compacted soils when inundated with distilled water. So if you just look at the mold that we use in this test, you would find some description about the mold that we use in the expansion index test. So mold containing an inner ring that is used for the compaction of the specimen for the expansion index test. The dimensions are mentioned in this particular slide. So expansion index test ASTM D4829-03, and you can see the various components of the mold assembly over here. This is the assembled mold, and here the mold assembly placed in the odometer, and this is the complete setup of the expansion index test. Test method. ASTM designation is D4829, so standard test method for expansion index of soils. The specimen is compacted into a metal ring so that the degree of saturation is between 49 and 51%, and the specimen and the ring are placed in a consolidometer. A vertical confining pressure of 1 psi is applied to the specimen, and then the specimen is inundated with distilled water. The deformation of the specimen is recorded for 24 hours or until the rate of deformation becomes less than 0.005 millimeter per hour. So some important things which are mentioned over here, that the degree of saturation is between 49 and 51%. Vertical confining pressure is to be applied equal to 1 psi, and the deformation of the specimen is recorded for 24 hours or until the rate of deformation becomes less than 0.005 millimeter per hour. So here you can see the formula of the expansion index, that is 1000 into H2 minus H1 divided by H1, or you can say it is equal to 10 into maximum percentage swell in expansion index test up to the end of the primary swelling. So H2, that is the height of the soil specimen at the end of swell, that is the primary swell, in inches or in millimeter. H1, the initial height of the specimen, that is 1 inch or 25.4 millimeter, and EI means the expansion index. So here you can see the behavior of the soil during the test, that you are having the percent swell along vertical axis, and this is the time. So you can see that along vertical axis we are having the percentage swell, and along horizontal axis the time. So you can see the curve. This is basically the log scale along horizontal axis. So we are having this type of shape. So this point is basically showing the end of the primary swell. So corresponding to that, you will have to note the height of the soil specimen, at the end of the primary swell. So this is the end point of the primary swell, and this is the secondary swell. Specimen preparation. First thing is adjust water content. Thoroughly mix the selected representative sample with sufficient distilled water to bring the soil to approximately optimum water content as determined in accordance with test method D698. The actual test method need not be run, but experience and judgment should be used to estimate that water content. After mixing, take a representative sample of the material for moisture determination and seal the remainder of soil in a close-fitting airtight container for a period of at least 16 hours or overnight. Weigh the moisture sample immediately and dry in an oven at 110 plus minus 5 degrees Celsius for at least 12 hours or in accordance with test D2216 to a constant mass to determine the water content. The moisture sample shall have a mass of at least 100 grams conforming with the test method D2216. Specimen molding. Form a specimen by compacting the cured soil in the 101.9 millimeter or 4.01 inch diameter mold into equal layers to give a total compacted depth of approximately equal to 2 inches or 50.8 millimeter. Compact each layer by 15 uniformly distributed blows of the rammer, dropping free from a height of 12 inches above the top of the soil when a sleeve type rammer is used, or from 305 mm above the approximate elevation of each finally compacted layer when a stationary mounted type of rammer is used. Scarify the first compacted layer before adding material for the second layer using a knife or other suitable object. During compaction, rest the mold on a uniform rigid foundation such as provided by a cube of concrete with a mass not less than 90 kg or 2000 pounds. Trim specimen. Following compaction, remove the upper and lower portions of the mold from the inner ring and carefully trim the specimen flush with the top and bottom of the ring with a straight edge. Determine initial height. Determine initial height of the specimen H1 to within 0.03 millimeter, that is 0.01 inch, or assume equal to the height of the specimen ring. Then comes the saturation. Calculate the water content and dry unit weight in accordance with the test method D698. Weigh the compacted specimen and determine the percent saturation. The percent saturation S may be determined as follows. So you can use this formula, and if you just look at this one, the different variables are involved. S, the degree of saturation percentage. W is the water content in percentage. G sub S, specific gravity of soil solid. Use 2.7 unless the specific gravity is known to be less than 2.6 or more than 2.8. Gamma W, unit weight of water, and you may take it as 9.81 kiloton per cubic meter or 62.4 pound per cubic foot. And gamma D, the dry unit weight, that is again a kilonewton per cubic meter or in pound per cubic feet. Well, when you are using this expression, here this one, the moisture content will be substituted in fraction, not in percentage, and you will be getting first degree of saturation fraction, then you can multiply it by 100 to get it in percentage. Adjust water content. Adjust the water content to achieve a degree of saturation of 50 plus minus 1%. If the degree of saturation is not between 49 and 51%, then remove the soil from the mold and adjust the water content by adding water or air drying. Repeat the steps until the degree of saturation of the compacted specimen is between 49 and 51. Now here you would find the procedure, and I need your attention. Place the soil specimen which has been compacted in the 101.9 millimeter or 4 inches diameter ring in a consolidometer or equivalent loading device with air-dried porous disc at the top and bottom. Place the specimen a total pressure of 6.9 kPa, that is 1 pound per square inch, including the weight of upper porous disc and any unbalanced weight of the loading machine. Allow the specimen to consolidate under this pressure for a period of 10 minutes, after which time make the initial reading D1 on the consolidometer dial indicator to an accuracy of at least 0.03 mm, that is 0.001 inches. Then inundate the specimen in distilled water, making periodic readings on the dial indicator for a period of 24 hours or until the rate of expansion becomes less than 0.005 millimeter per hour, or you can say 0.0002 inches per hour. However, in no case shall the sample be inundated and readings taken for less than 3 hours. Then remove the specimen from the loading machine after the final reading D2 and determine the change in height as the difference between the initial and final reading of the dial indicator using least count of the dial gauge. Determine the specimen mass to the nearest 0.1 gram. Calculation of the expansion index, that is E sub I or E sub I measured. So this is the formula: delta H over H1 into 1000. So what is delta H? Delta is the change in height, that is D2 minus D1 in millimeter. H1 the initial height, that is in millimeter. D1 initial dial reading in millimeter, and D2 is the final dial reading in millimeter. Report expansion index to the nearest whole number. So this point is very important. If the initial specimen height is greater than the final specimen height, report the expansion index as 0. So I will repeat this point. This is very important. If the initial specimen height is greater than the final specimen height, report the expansion index as 0, not as negative. The molding water content, the final water content, and initial dry density of the specimen shall accompany the expansion index in the complete presentation of results. Well, this slide is also very important. If the degree of saturation S is within the range from 40 to 60, the expansion index at 50% saturation is calculated from this formula. So I will repeat that if the degree of saturation S is within the range from 40 to 60%, the expansion index at 50% saturation is calculated from this formula. So you can see that different variables are involved. EI measured, that is measured expansion index corresponding to our degree of saturation. S measured, that is the degree of saturation determined by the test. And EI sub 50, that is the expansion index at 50% saturation. So this formula is very useful if you are not able to maintain the degree of saturation from 49 to 51, and the degree of saturation is falling somewhere in this range, so you can use this formula to get the expansion index corresponding to 50% saturation. Well, in this slide you can see one table. The classification of a potentially expansive soil is based on the following table. So based upon the expansion index value, we can comment on the potential expansion. You can see that if the expansion index is from 0 to 20, it means the soil is having very low swell potential. If it is 21 to 50, you can say low potential, 51 to 90, medium, 91 to 130, high. And if the expansion index is greater than 130, it means very high potential of swelling or expansion is present in that soil. So expansion index has become a very important parameter for the swelling soils, and based upon the expansion index we could be able to categorize different types of swelling soils or the expansive soils. So that's all about the expansion index. Thank you.